Hi, I am Sanjay Patel, and we are going to continue with our topic of subrings. We'll see some more results and examples in this video. First of all, I start with a very important example of subring, which is very useful. So let z plus dot, which is a ring of integers, be the ring of integers. Okay, and let me take n belongs to say z, n belongs to z, be any fixed integer, okay, and define a new set, say capital S, which is denoted by the symbol n into z, and it consists of all multiples of n. So say n into 0 will be 0. If you take n into 1, you will get n into minus 1, you will get minus n. So it contains plus or minus n, plus or minus 2n, plus or minus 3n, like that. Okay, so it is nothing but set of all integers of the form, say m into n, where m belongs to z. And remember, this n is fixed. For example, if n is equal to 3, you will get 0 plus or minus 3n plus or minus say 6n plus or minus 9n, means all multiples of 3. Okay. The problem is very simple. Prove that this nz is a subring of the ring of integers. Okay. The solution is very simple. So let us write systematically, as it is very important example. So first thing, you note that this S is non-empty. Here you can say 0 belongs to the set S, okay, that is nz, and therefore the set S is non-empty. That is my first result. Secondly, I take two elements, say A and B belongs to S. Let A and B belong to S be arbitrary. Means A and B are any two elements in the set nz. So therefore we can write, as A belongs to S and all elements of S are of the form, say n into something, that something is some integer, I can say that A is of the form n into say m1, and B, or let me write some other things, n into m, and B is equal to n into k for some integers, say m and k belongs to z. Okay, so this implies, if I write now A minus B, that is n into m minus n into k, which can be expressed as n into m minus k. This m minus k is also an integer because m and k are integers. So therefore we can express a minus b in the form n into say p, where p is m minus k and it is an integer. So the conclusion is this element is also a member of the set nz, means the set S. So what I have proved is, for all A and B belong to the set S, implies A minus B also belongs to S. So this is my result number 2. The third condition which is to be proved for making S into a subring is that it is closed with respect to multiplication. So let us take A and B belongs to the set S, which is n times z. Okay. And what I want to prove here is that A into B also belongs to S. Since A belongs to S and B belongs to S, I can write A is equal to say n into m and B is equal to n into k, where m and k are some integers. Then if you find the product of these two, A and B, I will get nm multiplied by nk, which I can write as n times m into n into k. M and k all are integers, so this is of the form n into say p, when p is a integer, that is it is an element of z. So we can conclude that A into B is also a member of the set nz. This belongs to S, means nz. So what is proved is, for all A and B belongs to the set S implies A into B belongs to S. Result number 3. So in 1 we have proved it is non-empty. In 2 we have shown that for every AB belongs to the set S. For every AB belongs to S. Just a minute. For every A and B belongs to S, A minus B belongs to S. And in 3 we have shown that for every B belongs to S, A dot B belongs to S. So from 1, 2 and 3, it follows that the set S equal to nz is a subring of the ring of integers, of the ring of integers z. Okay, so as a result of this interesting example, an important example, we have now infinitely many subrings of the ring z. Just take any integer n and all multiples of that integer forms a subring. Okay, now let us discuss some few things about the subrings. The first thing I want to say is that if the main ring R is commutative, if the ring R plus dot, the main ring, is commutative ring, then it is obvious that every subring of R is also commutative. In short, every subring of a commutative ring is commutative. Secondly, the same zero element, the zero element which is in R, it is also in the set subring S, if S is a subring. Okay, but the third important thing I want to mention here is this need not be true for the unity element. If a ring R has a unity element, say 1, then the subring, or then every subring rather, then every subring S of R need not have first of all the unity element, need not have unity, or even if it exists, even if unity exists, it need not be the same. Let me write this way. Or if R has a unity element 1, then every subring S of R need not have unity. Also I can say the unity, or the unity of S may be different than the unit of that of the ring R. Let me explain both of this. There are two things here. Okay. For both of this, I will take examples. If a ring R has unity, for example, the ring Z plus dot, the ring of integer, this has a unity element 1. Okay, 1 is an integer in Z and it is a unity element, means identity element for multiplication. A into 1 is equal to A for every A belongs to Z. Okay, but if I take the subring S equal to say 2Z, that is all the even integers 0 plus or minus 2 plus or minus 4 plus or minus 6, all the multiples of 2, we know it is a subring, but this subring has no unity element. So even if unity exists in the main ring, it need not be in its subring. Second thing I want to mention here is this. It may happen that unity of the ring and the unity of the subring are different. Okay. For example, let me take the ring of say residue classes modulo 10. Let R is equal to the ring Z10. That is, the ring I'm taking here is Z10 plus 10 and dot 10. The ring of residue classes. You know what is Z10? It contains the residue classes 0, 1, 2, 3 and so on up to class 9. These are the elements. There are 10 elements in Z10. This is a ring. And let me take one subset of this R. Let capital S is equal to class 0, class 2, class 4, class 6 and class 8. Okay. Then with respect to the same operations, we can prove that it is a subring of the ring Z10. What you can do here is you can prepare the table for the same operation. The same operation, plus is equal to plus 10 and dot is equal to dot 10. So if I take say this plus 10 and write all the elements, let me write without the square brackets, 0, then 2, then 4, then 6 and then 8, and 0, 4, 2, 6. Let me make it bigger. I should have 0, 2, 4, 6. Oh, I want one more. So 8. Okay, let me extend this. So you can prepare the comparison table or multiplication table for this set and check 0 plus 0, 2, 4, 6, 8. This is very, very simple. We have already understood. And 2 plus 2 is 4. 2 plus 4 is 6. 2 plus 6 is 8. 2 plus 8 is 10 and 10 means 0. 4 plus 2 6. 4 plus 4 8. 4 plus 6 10 and 10 is equal to 0. 4 plus 8. 4 plus 10 8. 4 plus 8 is 12 and 12 modulo 10 is 2. So again we will get 2 here. Again 6 plus 2 8. Then 4 6 are 24. And just a minute, sorry, 6 plus 4 10 and 10 equal to 0. 6 plus 6 12, so it is 2. 6 plus 8 14, so 4. Here also we can write 8 plus 2 10, so 0, then 2, then 4, then 6. So you can see from this it satisfies all the condition for operation of addition. Same way I can prepare the table for multiplication. So let me prepare a table for multiplication. Multiplication modulo 10. So first is 0, then 2, then 4, then 6, and say 8. Let's take 8. Okay. And again 0, 2, 4, 6, 8. Okay. And let us put the values here, 2, 4, 6, 8. And now we have to use this operation of multiplication modulo 10. If you multiply any element with 0, you will get 0. So let me fill up all this with 0, 0, 0. 2 to the 4, 2 4 the 8, 2 6 the 12 means 2, 2 8 the 16. 16 is what? 6. 16 modulo 10 is 6. Then 4 to the 8, 4 4 the 16 means 6, 4 6 the 24 means 4, 4 8 the 32, so it is 2. Again here I will get 6 to the 12, so 2, 6 4 the 24, so that is 4, 6 6 the 36, 6 8 the 48, so it is 8, 8 is a 16, so 6, 32 means 2, 8 6 the 48 means 8, and 8 8 the 64 means 4. So this is the table for multiplication. So from these two tables, it is clear that the set S with respect to addition modulo 10 and multiplication modulo 10 is a ring, and this is a subset of Z10. So I can say that this S is a subring of the ring Z10, the ring of residue classes modulo 10. You know, in Z10 we have identity element. In Z10 we have unity element. For multiplication is class 1 because class A dot 10 into class 1 is always equal to class A. For every class A belongs to Z10. So this is unity element, right? This is known to you. But if you see that this class 1 is not a member of our set S, class 1 is not there. So unity of the ring R is not an element of the set S. But if you observe this very carefully, this multiplication table, observe this table very carefully, then you can find another element which behaves like an identity element for multiplication. What to check for identity element for multiplication? Suppose if I consider this element 2, then you see 0 into 2 is 0, 2 into 2 is 4, so this is not working as identity element, so that is not useful. Like 4 into 2 must be 4, but I am not getting that. This I cannot take as identity element. But if I take this element, say 6, let us observe. For identity element, what you should check is just you should get the copy of the title row or title column in front of or just below that given element. For example, if I am concentrating on this 6, then what should I get here? Below 6 is the copy of this title column, and it is so. Yes, 0 to 0, 2 to 2. That means x dot 10 into 6, 6 means class 6, is equal to x for every x belongs to the set S. The same way, if you take 6 here in this row, if you fix this, then you must get the copy of the title row, that is 0 to 0, 2 to 4, 4 to 4, 6 to 6. So yes, so this means that we are getting class 6 dot 10 into x is also equal to x for every x belongs to S. So that means this 6 is behaving as an identity element in this new set S. So class 6 is the multiplicative identity in the subring S. Okay, but the set means the element class 6 is the unity of S. Okay, because x dot class 6 is equal to x is equal to class 6 dot x for every x in the set S. So this example shows that unity of the subring may be different than that of the original ring. Okay. Now let us go to the next interesting thing about if you have many subrings, what can you say about the union or intersection of these subrings? In this regard, we have a theorem or a result, you can say, that if you take any two subrings, then their intersection is always a subring. So prove that intersection of any two subrings of a ring is also a ring. This you can generalize also for many rings, infinitely many rings. Let me prove this result. First we'll formulate, let R plus dot be a ring, and suppose capital S1 and capital S2 are two subrings of the ring R. Okay. What I want to prove is that intersection is also a subring. So our aim is to prove S1 intersection S2 is also a subring. Okay, S1 intersection S2 is also a subring. So we must show that it is non-empty set and it satisfies the two conditions which we have proved in our necessary and sufficient condition for a subring. So first of all, let us start with the fact that since S1 and S2 are subrings, it contains zero elements. I mean, 0 belongs to S1 and the zero element of the ring R also belongs to S2. So I can say that 0 belongs to S1 intersection S2, and that means S1 intersection S2 is non-empty. This is my first remark. Now I will prove that it is satisfying that condition. So let us take two elements. I want to show that S1 intersection S2 is a subring. So I am starting with two elements in S1 intersection S2. Any two elements. We don't know what is this. So let A comma B belongs to S1 intersection S2 be any two elements. This means that A and B are in S1 and also A and B are in S2, because intersection means it contains all elements in S1 as well as S2. But S1 and S2 are subrings, so it is closed with respect to that addition and multiplication. So I can say that A minus B belongs to S1 and A minus B belongs to S2 because S2 is a subring. So it satisfies that condition. So this implies, I can say, that A minus B is a common element of S1 and S2, means it is in the intersection. So what is proved here is, for every A and B belongs to S1 intersection S2, we have proved that A minus B also belongs to S1 intersection S2. So this is my result number 2. Okay. And the third result goes similarly. About multiplication operation. So again we start with any two elements A and B belongs to S1 intersection S2. That implies A and B belongs to S1 and A and B also belongs to S2. Since S1 and S2 are subrings, we can say immediately A dot B belongs to S1 and A dot B also belongs to S2. Again the same reason, because S2 is a subring. So it is closed with respect to multiplication. If X belongs to S1 and X belongs to S2, it means X belongs to S1 intersection S2. So I can say that A dot B belongs to S1 intersection S2. So what I have proved here is, thus, for every A and B belongs to S1 intersection S2 implies A dot B also belongs to S1 intersection S2. This is my third result. First result we have proved is it is non-empty. In the second result, S1 intersection S2 satisfies the closure property of addition and additive inverse. And the third condition says it is closed with respect to multiplication. So from 1, 2 and 3, we have S1 intersection S2 is a subring of R. So what I have proved is intersection of any two subrings is always a subring. And this we can generalize for any number of rings. So in general, I can say if S1, S2, dot, 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 up to Sn are subrings of a ring R, then intersection of all these, that is intersection I is equal to 1 to n of Si, is also a subring of R. Okay. Another thing is, this result is not true for the union. So the above theorem or the above result is not true for the union. Means if you take union of any two subrings, then it need not be a subring. That is, a union of any two subrings of a ring R need not be a subring. Okay, union of any two subrings need not be a subring. And whenever we say something is not true in mathematics, we must provide some counter example for this. And we are already having that counter example in our hand. In the beginning of this lecture, if you remember, we have mentioned that this ring R of integers, if I take z plus dot, I will write like this. It is not proper, but still it is understood. R means ring, and we are taking ring is equal to the ring of integers. We'll write in short. This is the ring of integers. And let me take two subrings. We know infinitely many subrings of this. If you take any integer n, then all multiples of n is a subring. So I am taking S1 is equal to one subring and S2 is equal to another subring from the ring R. So let us take S1 is equal to 2z, that is 0 plus or minus 2 plus or minus 4 plus or minus 6 and so on. Okay, and S2 I am taking as 3z, that is 0 plus or minus 3 plus or minus 6 plus or minus 9 and so on. all multiples of 3 and all multiples of 2. Okay, we have already proved that S1 and S2 are subrings. So I'm writing, we know that S1 and S2 are subrings of the ring Z. Okay, of the ring Z. Now, if I take S1 union S2, that is this 2Z union 3Z. So it contains all these elements, all these multiples of 2 and all multiples of 3. Okay, but then this is not a subring. This is not a subring. Why? Because if you take two elements from S1 union S2, say let us take A is equal to 2 and B is equal to 3 belongs to S1 union S2, that is 2Z union 3Z. I am taking two elements from S1 union S2. Then if you find A plus B, that is 2 plus 3, which is equal to 5, which is not in S1 union S2, because S1 union S2 contains either a multiple of 2 or a multiple of 3, and 5 is not a multiple of 2 or a multiple of 3. So clearly I can say S1 union S2 is not closed. It is not closed with respect to the operation of addition. So this implies S1 union S2 is not a subring. So remember, union of two subrings need not be a subring. Okay, and at the end of this lecture, I am giving you an interesting problem to solve yourself, as to prove that S1 and S2 be any two subrings of a ring R plus dot. Okay, then prove that S1 union S2 is a subring, is also a subring of R if and only if we have either S1 is subset of S2 or S2 is subset of S1. So this you can try. It is an interesting exercise for you, and if time permits, we'll be discussing this in our last lecture of mixed examples of rings. So till then, say goodbye and thank you.